In statistics, the Maxwell-Boltzmann distribution is a particular probability distribution named after James Clerk Maxwell and Ludwig Boltzmann. It was first defined and used in physics for describing particle speeds in idealized gases where the particles move freely inside a stationary container without interacting with one another, except for very brief collisions in which they exchange energy and momentum with each other or with their thermal environment. Particle in this context refers to gaseous particles, and the system of particles is assumed to have reached thermodynamic equilibrium. While the distribution was first derived by Maxwell in 1860 on heuristic grounds, Boltzmann later carried out significant investigations into the physical origins of this distribution. A particle speed probability distribution indicates which speeds are more likely. A particle will have a speed, selected randomly from the distribution, and is more likely to be within one range of speeds than another. The distribution depends on the temperature of the system and the mass of the particle. The Maxwell-Boltzmann distribution applies to the classical ideal gas, which is an idealization of real gases. In real gases, there are various effects that can make their speed distribution different from the Maxwell-Boltzmann form. However, rarefied gases at ordinary temperatures behave very nearly like an ideal gas, and the Maxwell speed distribution is an excellent approximation for such gases. Thus, it forms the basis of the kinetic theory of gases, which provides a simplified explanation of many fundamental gaseous properties, including pressure and diffusion. Distribution function. The Maxwell-Boltzmann distribution is the function whereas the particle mass n is the product of Boltzmann's constant and thermodynamic temperature. This probability density function gives the probability, per unit speed, of finding the particle with a speed near. This equation is simply the Maxwell distribution with distribution parameter. In probability theory, the Maxwell-Boltzmann distribution is a chi-distribution with 3 degrees of freedom and scale parameter. The simplest ordinary differential equation satisfied by the distribution is, or in unitless presentation, typical speeds. The mean speed, most probable speed, and root mean square can be obtained from properties of the Maxwell distribution. The most probable speed, Vp, is the speed most likely to be possessed by any molecule in the system and corresponds to the maximum value or mode of f. To find it, we calculate the derivative df, dv, set it to 0 and solve for v, which yields, where R is the gas constant and m equals n, m is the molar mass of the substance. For diatomic nitrogen at room temperature, this gives meter per second. The mean speed is the expected value of the speed distribution. The root mean square speed is the second-order moment of speed. The typical speeds are related as follows. Derivation and related distributions. The original derivation in 1860 by James Clerk Maxwell was an argument based on demanding certain symmetries in the speed distribution function. After Maxwell, Ludwig Boltzmann in 1872 derived the distribution on more mechanical grounds by using the assumptions of his kinetic theory of gases, and showed that gases should over time tend toward this distribution, due to collisions. He later derived the distribution again under the framework of statistical thermodynamics. The derivations in this section are along the lines of Boltzmann's 1877 derivation, starting with result known as Maxwell-Boltzmann statistics. Maxwell-Boltzmann statistics gives the average number of particles found in a given single particle microstate, under certain assumptions, where I and j are indices of the single particle microstates. N is the average number of particles in the single particle microstate I. N is the total number of particles in the system. A is the energy of microstate I. T is the equilibrium temperature of the system. K is the Boltzmann constant. The assumptions of this equation are that the particles do not interact, and that they are classical. This means that each particle's state can be considered independently from the other particle's states. Additionally, the particles are assumed to be in thermal equilibrium. The denominator in equation is simply a normalizing factor so that the n add up to 1. In other words, it is a kind of partition function. Because velocity and speed are related to energy, equation can be used to derive relationships between temperature and the speeds of gas particles. All that is needed is to discover the density of microstates in energy, which is determined by dividing up momentum space into equal-sized regions. Distribution for the momentum vector. The potential energy is taken to be zero, so that all energy is in the form of kinetic energy. The relationship between kinetic energy and momentum for massive non-relativistic particles is where p2 is the square of the momentum vector p equals px, py, pz. We may therefore rewrite equation as where z is the partition function, corresponding to the denominator in equation. Here m is the molecular mass of the gas, T is the thermodynamic temperature and K is the Boltzmann constant. The normalizing constant C can be determined by recognizing that the probability of a molecule having some momentum must be 1. Therefore the integral of equation over all px, py, and pz must be 1. It can be shown that substituting equation into equation gives the distribution is seen to be the product of three independent normally distributed variables, and, with variance. Additionally, it can be seen that the magnitude of momentum will be distributed as a Maxwell-Boltzmann distribution, with the Maxwell-Boltzmann distribution for the momentum can be obtained more fundamentally using the H theorem at equilibrium within the kinetic theory of gases framework. Distribution for the energy. The energy distribution is found imposing where is the infinitesimal phase space volume of moment corresponding to the energy interval. Making use of the spherical symmetry of the energy-momentum dispersion relation, this can be expressed in terms of as using the n, and expressing everything in terms of the energy we get. And finally, since the energy is proportional to the sum of the squares of the three normally distributed momentum components, this distribution is a gamma distribution. In particular, it is a chi-squared distribution with 3 degrees of freedom. By the equipartition theorem, this energy is evenly distributed among all 3 degrees of freedom, so that the energy per degree of freedom is distributed as a chi-squared distribution with 1 degree of freedom, whereas the energy per degree of freedom at equilibrium, this distribution will hold true for any number of degrees of freedom. For example, if the particles are rigid mass dipoles of fixed dipole moment, they will have 3 translational degrees of freedom and 2 additional rotational degrees of freedom. The energy in each degree of freedom will be described according to the above chi-squared distribution with 1 degree of freedom, and the total energy will be distributed according to a chi-squared distribution with 5 degrees of freedom. This has implications in the theory of the specific heat of a gas. The Maxwell-Boltzmann distribution can also be obtained by considering the gas to be a type of quantum gas. Distribution for the velocity vector. Recognizing that the velocity probability density Fv is proportional to the momentum probability density function by and using P equals mv, we get which is the Maxwell-Boltzmann velocity distribution. The probability of finding a particle with velocity in the infinitesimal element dvx, dvy, dvz about velocity v equals vx, vy, vz is like the momentum. This distribution is seen to be the product of 3 independent normally distributed variables, but with variance. It can also be seen that the Maxwell-Boltzmann velocity distribution for the vector velocity vx, vy, vz is the product of the distributions for each of the 3 directions. where the distribution for a single direction is each component of the velocity vector has a normal distribution with mean and standard deviation. So the vector has a three-dimensional normal distribution, a particular kind of multivariate normal distribution, with mean and standard deviation. The Maxwell-Boltzmann distribution for the speed follows immediately from the distribution of the velocity vector above. Note that the speed is in the volume element in spherical coordinates, where under the course and path angle. Integration of the normal probability density function of the velocity above over the course and path angle, with substitution of the speed for the sum of the squares of the vector components, yields the speed distribution.